Hi, everyone. Thanks very much for joining today. My name is Patrick Goulding. I'm an applications engineer with Altair, and I'm going to be talking today about our system modeling and system integration tool, Altair Activate, used for modeling system dynamics and controls. So our agenda today will be in about a 40-minute webinar to go over an overview of Altair Activate, and then talking about physical component modeling, specifically mechanical system components using Modelica, which are a set of blocks that we utilize with Altair Activate for physical component modeling. And then we're going to talk specifically about vehicle dynamics, how to model vehicle dynamics in Activate in sort of a low-key level, and then taking that model that we use as an example and putting it into a larger context, a slightly more complex model for management of energy consumption in a vehicle. And then I'll just close out with some learning resources that you can utilize for learning a bit more about in-depth of modeling, system modeling with Altair Activate. So what is Altair Activate? Activate is a system modeling tool, yes. It is also an open integration platform. And we like to make sure that our users understand that, it can and should be used as an integration tool for subsystems designed in various disciplines and also designed using various tools. So you can design subsystems in Activate using a mathematical approach, using just scripting, and it embraces many languages for scripting. C code, SPICE for electronic modeling, component modeling, Modelica for physical components, Python, and our own open matrix language, OML, which is a matrix-based language for mathematical scripting. And also the approach for modeling that may first come to your mind with system modeling would be the block diagram approach, or a 1D approach, we like to call it. So this would be utilizing signal blocks for the sharing of, or the connection of signals between blocks, creation of a signal, using those values entering as input into another block, output another value, and so forth. Also physical component modeling using Modelica, and electric and electronics using our set of SPICE blocks as well. And with Altair Activate, you also have the opportunity for co-simulation with our multi-body dynamics tool, MotionSolve, also with our low-frequency electromagnetics tool, Flux, and utilizing the functional mock-up interface, or FMI standard. You can co-simulate with any outside third-party tool that embraces the functional mock-up interface. So any other third-party tool with which you could export a functional mock-up unit or a subsystem, you can bring in that functional mock-up unit into Activate and co-simulate with that subsystem as well. So many different domains or ways in which you could model systems or subsystems in Altair Activate, and you can bring them all into one shared diagram. So in this regard, it is an integration platform that also incorporates linearization of subsystems and ways to use optimization as well. This idea of modeling in a 0D, 1D or 3D manner. I'll talk about a little bit in the upcoming slides. Just to hit on it again, 0D is the sort of mathematical approach, or a system of equations to represent a mechanical system, let's say. A 1D approach would be that drag and drop block diagram system modeling sort of way. And then the 3D would be if you're co-simulating with a model-based tool, a 3D model, and using that as a subsystem in your system model. Using these different types of modeling, 0D, 1D, 3D, you can design all types of systems in Activate, from multi-body dynamics to control systems, motor control, using low-frequency electromagnetic analysis, and high-frequency electromagnetic analysis as well, bringing in output results from our tool FEKO for high frequency, as well as structural analysis, bringing in flexible bodies in MotionSolve. There are various reasons that you might want to design using a set of mechanical equations for a multi-body system versus a 1D signal-based approach versus a 3D co-simulation. If we're thinking about multi-body dynamics, this set of equations would look something like this, scripted using our open matrix language. But you can choose to model that exact same system using our Modelica library for physical mechanical components, and that would look something like you're seeing in the middle here. And for the highest fidelity solution, we're talking about bringing in a co-simulation, a MotionSolve block, with a mechanical system designed in motion view using MotionSolve, and then sending signals co-simulating with that mechanical system for your highest fidelity analysis. So let's take a look at the user interface for Altair Activate. It's very user-friendly, I believe. The ribbon on the top allows you to open new models, and using that view drop-down menu, you can see the different windows that are available to you in the user interface. A project browser, a property editor for editing things like the color scheme of plots of your signals, a variable browser, and a really nice demo browser on the bottom left, which is a great way to explore the tool by pulling in, bringing up some of our demo models organized in various domains, so you can get an idea of how you might go about building a similar type of model. There's a command window, an OML command window at the bottom for scripting with open matrix language or Python as well. And then our palette browser on the right, so you can navigate through our sets of blocks, like this constant block for generating a signal of a constant value, step generators, sine waves, and so forth. And this Modelica browser for our Modelica components. And those are subcategorized into electrical, mechanical, magnetic components, and so forth. And so I'll just pull in a couple Modelica components as an example. This is a spring and damper. And then you can connect things like the spring and damper to a mass for defining a mass that is acting on that spring and damper. And your modeling window allows you to navigate through the several levels of your model. This is a hierarchical modeling approach, so you can zoom in to subsystems and back out again, and then connecting your inputs and outputs with your linkages. So let's take a look at an example of a mechanical model in Activate. So we're going to use the example of an active suspension. If you're going to model an active suspension in Activate, you can start with what we call a quarter car model, which is zooming into, instead of all four wheels, zooming into just one wheel system. And looking at the diagram on the right, we can break this down into 4 simple equations that define our system states. And the system states that we're interested in this example are really a set of 2 different displacements and 2 different velocities. So our tire deflection is the difference between the displacement of the road and then the displacement of our unsprung mass, which is the first mass above the displacement of the road. And then our unsprung mass velocity, which is, the rate of change of that displacement over time. And then the suspension stroke, which is really the displacement of the suspension mass. And we define that as the difference between the displacement of that sprung mass and the displacement of the unsprung mass. And then the sprung mass velocity, the rate of change of that sprung mass. So if we look at a system model of this active suspension, that diagram of the sprung and unsprung mass of really those 4 states is enveloped in this blue block there, the quarter car model, that also encompasses the control system as well. So if we take a look inside that blue block, sort of zooming into that block, we'll see our suspension system, which is modeled using Modelica components. And it looks very similar to our diagram, right? And that's because of the way you can utilize Modelica blocks, the way they interact and share information with each other allows you, it's an acausal way of modeling, but it allows you to make your system look very much like it would in sort of a diagram that we saw. So included in this Modelica system, we see our road velocity input, our road velocity signal coming into our system here, outlined in yellow. And then that suspension system, like I talked about, looking exactly like our diagram. So we have blocks for our masses that define our masses. And double-clicking on those blocks will allow you to set the parameters of that mass, which is just a value of the mass. Our 2 spring and dampers. And double-clicking on those allows you to set the spring coefficient and the damping coefficient. Our actuator force, which is the signal coming in and acting on the upper suspension, the sprung spring and damper, which is our control force. And that makes it an active suspension rather than a passive one. And then we're measuring these 3 things, our suspension stroke, our sprung mass velocity, and our sprung mass acceleration. So using this approach of utilizing Modelica physical component blocks in order to model an active suspension, compared to if we used a 3D model, a co-simulation with multi-body dynamics 3D tool like MotionSolve, it allows us to run this model very quickly and to run many iterations of this model in order to, for instance, tune a control system. And when you're tuning a control system, if you have experience doing so, you know that it takes many iterations, many times running that model in order to measure the response of your system, and then to tune it a bit further, tune your control gains. So you want a model that runs very quickly, and Modelica models run quite quickly, and so do a mathematical 0D model as well. So this is a case where the fidelity of the system that you're modeling can have a large impact on your ability to design your control system. So your output for something like this to measure the effectiveness of your active suspension system would be measuring the sprung mass accelerations using, in this case, 3 different types of an active suspension. Active suspension with soft, moderate, and firm gains. And so you can measure the response of your system and decide what are the best parameters of your active suspension system. So now let's take a look at modeling some simple vehicle dynamics in Activate. So if we're talking about vehicle dynamics, let's break it down or distill it into just sort of the simple vehicle dynamics. So a summation of the forces that we're interested in. And then we'll add in some real values here and then take a look at a system model in Activate of this. So the forces that we're interested in are the driving force, which is coming from the engine, right, producing torque and driving the vehicle forward. And then the forces working against it, which are a braking force when the driver is applying a brake, the force due to friction, which is the tires against the road, and then the drag force of the air acting against the windshield of the vehicle. So this makes up sort of the summation of forces that we're interested in modeling. So for instance, if we take a look at the driving force, we have our driving torque. We're giving that a value of 200 Newton meters. And then we're taking into account the wheel radius, because the driving torque multiplied by the inverse of the wheel radius gives us our forward drive force. And then we break down the braking force, the rolling friction, and then the drag force as well here. But let's use these values and then take a look at a system model that incorporates these. So here we are in Activate. This is Activate, the latest version, 2021.1. And we have here a system model of a vehicle with input of a driving cycle. So this is a speed versus time drive cycle that's going to command this vehicle to move while the vehicle experiences the dynamics that we saw in the slides before, the forces against it due to friction, braking, and drag force. And then this vehicle, we're going to measure the energy consumption for this vehicle to follow this drive cycle while under the influence of these external forces. So I can go ahead and play this. I can run this model up in the top ribbon using this play button. And when I do so, this model pulls up a little user interface, a little GUI, with which I can use to enter the parameters of the vehicle. So the mass of the vehicle, the aerodynamic cross-section that's used in the calculation of the drag force, the braking force, and so on. And when I hit OK, it runs this model, and I can see that it ran very quickly, and it's output my results here. And the results that I'm I'm mapping, for one, this is the drive cycle on the top. So the speed versus time, and then the energy consumption in kilowatt hours across the distance traveled. So let's take a look inside this model and see how we came up with this and see how it's modeled. So I can zoom into this car subsystem and see that it starts with a driver. And if I go into this driver block, I see that I have my input signal, which is my drive cycle, the desired speed, the velocity of this vehicle, and then a simple KI controller, or sorry, a PI controller, proportional and integral controller, in order to sort of for this that models the engine to maintain the desired speed with our actual speed, to match our desired speed to our actual speed, and try to maintain that while the forces acting against it are occurring. So those are the disturbances. And then our driver applies basically an acceleration, the gas pedal, and sends an acceleration signal to our engine subsystem. So we can look inside that. And we have a simple engine, which is modeled using Modelica blocks. And again, I'll show you on the palette browser on the right side, we can go into our Modelica block library. And these are mechanical blocks pulled from the mechanical set of blocks, and translational. And then if I go back again, go into the rotational and components, and we can see some of these blocks that were used to model the engine. So this is an inertia block. We have a torque block, which converts our torque signal into a torque applied to our small mechanical system. And a lookup table here. So we have our accelerations coming from our gas pedal, which is going into a lookup table, which is an acceleration versus torque table. So from that, then the output of this will be our torque applied. So output from our engine subsystem, we have our rotational velocity of essentially the drive shaft between these two blocks here. And our rotational velocity signal enters as input into our differential. So we can take a look at our differential, modeled again with rotational mechanical blocks from the Modelica library. So we have our input rotational velocity signal coming in here, moving into an ideal planetary gear. And using this and a couple other inertia blocks, we have our differential modeled, which then essentially, splits our rotational velocities from the drive shaft to our two wheels, our right wheel and our left wheel. Moving into those, what does a wheel do? It turns rotational velocity into translational velocity, and that's what we see here. So another lookup table, which is used to turn our brake signal from the driver into an opposite force. So this is our brake force applied against the the forward translational force applied by this rolling wheel block, and then our friction force as well. So we have a block here which is support friction, which applies friction based on our parameters of friction, working as well against the wheels, against our driving force. So output from this wheel subsystem is our translational speed. Okay, so now we can measure our forward speed of the vehicle which is a summation, the forward speed, using or taking into consideration friction and our brake force here. So you see how we're adding together, we're compiling sort of our dynamics, our vehicle dynamics, our set of 4 states that we saw in the previous slide. So now moving to the right in our system diagram, we have our driving resistance, or our drag force. So here we have an equation which calculates based on air density what the drag force would be, and it's applied, is fed into a force block, again working against the vehicle mass and our translational speed. So in this block here, in this subsystem, we incorporate the drag force working against the vehicle and outputting our vehicle speed that's now incorporating our drag force as well. So if we zoom out again and zoom out completely, our vehicle speed is now fed back into our driver as our actual speed. And so the driver, that sort of simple control system in the driver, is taking into account our actual speed and trying to match it to our desired speed. So we've used this model of a simple vehicle in order to measure the energy consumption during a drive cycle. Now let's use this simple example and take it into a larger context, a larger application of a hybrid electric vehicle where the energy needs to be managed in order to determine whether power should be used by the battery, the energy stored in the battery, or the vehicle should be powered by the internal combustion engine. Let's take another look at our vehicle dynamics equations, and we can remind ourselves how they were applied in this last system model. So we have our set of forces. The driving force, F drive, which is the drive torque multiplied by 1 over the wheel radius, which gives us our driving force. This was applied via the driver block, which creates an acceleration signal in order to maintain our driving profile, our velocity profile, which sends a signal to the engine to apply this force, this torque, onto the drive axle, the powertrain. And the brake force is a signal that's sent by the driver block, the brake signal, but the actual force is applied within the right and left wheel blocks. So we saw that as a Modelica force block, which applies a force in the opposite direction of the driving force. And then the rolling friction was also in these right wheel and left wheel blocks, which was a rolling friction Modelica block, provided the mass of the car and the friction coefficient. And in essence, it applies an opposite force, again, in the opposite direction of the driving force. And then our vehicle drag, the drag force, which existed within this driving resistance block, takes into account some parameters like the cross-sectional area, the drag coefficient, and the air density. And in the end, applies another force opposite to our driving force. So the summation of all of these makes up our vehicle dynamics. So now let's see how these are applied in a more complex hybrid electric vehicle model. So here we have our hybrid electric vehicle powertrain model. And this one takes what we learned about the vehicle dynamics and then applies it into a more complex model that will tell us something about the energy management of this vehicle as it goes through this drive cycle. So let's go ahead and run the simulation. And again, it runs quickly because it's really just using more of an analytical approach rather than a 1D approach, rather than a co-simulation with 3D models. So the first output that we get here is our engine fuel consumption. So this, is a function of the work performed by the internal combustion engine in this hybrid electric vehicle. So the fuel consumption over time. And then it also, we see the behavior of the state of charge of the battery. And this being a function of the work required by the battery to produce the forward driving force of this vehicle. And of course, the battery, you see the battery usage as the state of charge diminishes. And then also this battery is being recharged at times by the engine, as happens in hybrid electric vehicles, to recharge the battery at moments to maintain, a positive state of charge throughout the drive cycle. So let's take a look inside this model and see how we get that behavior. So on the left side, we see this drive cycle that we had in the other, similar to what we had in this other model. So this is producing a desired velocity over time that this vehicle has to maintain. And then this purple block here, I'll zoom in. This is basically what our previous model was to a large extent. If I go inside, we go a couple levels deep in here. And then I'll open up the diagram context up in the top left here. So this is some syntax that provides us the model parameters that are used inside this equation for the vehicle dynamics. The vehicle dynamics, which will output the power required to maintain our forward drive force. So the model parameters consist of things like the mass of the vehicle is defined here, the air density, the drag coefficient, things that we remember seeing in our force equations, right? The frontal cross-sectional area, these go into the calculation of the drag force. We're going to take into account the road angle, the gradient of the road or the incline, coefficient of rolling friction, wind velocity. So all of these parameters are defined in this diagram context. And then if we look at this equation here, so we see there are two signals coming in: the desired speed, which is coming straight from our driver, the driving profile that we want to maintain. So our desired speed and desired acceleration. These are going to be two values used in this equation to output the power required. So there are a few parts to this equation, and if we pull them out, we can recognize parts of our vehicle dynamics model. So M is the mass of the vehicle. U2 is our second input, which is the acceleration. So mass times acceleration will be our desired forward force, our driving force of the vehicle. And then this second part here, I see the drag coefficient. A is the cross-sectional area of the front of the vehicle. UW is our wind velocity. So this makes up the calculation for the drag coefficient. And then this third entity here, this third entry is the frictional calculation, the rolling friction. And then the extra effort it'll take to take into account the incline of the road, the gradient of the road. So all of that will output our force required in order to maintain our desired speed. So if I back out to the top level of this diagram again, that block is outputting our force required, or our power demand. And then we go into this block that is called the Supervisory Controller. And so the goal of this block is to decide whether to have the battery provide the power necessary in order to produce our forward driving force, or whether to engage the internal combustion engine in order to produce that forward force, driving force. So if I look inside our supervisory controller, before we enter into it, we see that it's receiving as input the state of charge of the battery at every time step, at every moment, and also this power demand coming from our required power vehicle block. So now we'll move inside of this, and we see with a nice little diagram up here that this is a series hybrid system. And this, so with a little bit of logic here, control logic, this part of the system decides based on the demanded power at every moment, whether to engage, whether to pull the power from the battery, power demand from the battery, or whether, because of maybe the state of charge of this battery at this moment, if it's too low, if it's under a certain threshold, it won't engage the battery. It will require power from the engine instead. And so this is a little bit of logic that makes up this supervisory controller of our hybrid electric vehicle. So it will either demand power from the internal combustion engine or from our battery. And this also decides whether the state of charge of this battery is below a certain threshold. It will demand extra power from the battery in order to recharge this battery, to regenerate power, stored power in the battery cells. So coming out of this block, we've got power demand from the engine, which goes into this internal combustion engine block, and power demand from the battery. The power demand from the battery goes into this our battery super block. And if I zoom in here, we have a fairly complex set of logic and signal blocks to model this battery. But in short, it takes into account discharge losses, charging losses, and based on the power demand, the demand that we're requiring of this battery, and then also power coming from the internal combustion engine in order to recharge the battery, we're updating our state of charge at every moment. The amount of power remaining, the amount of energy remaining in this battery. And then in our engine block, We have our power demand, and then a simple lookup table that allows us to calculate or to determine the fuel consumption based on our power demand at every moment in this simulation. So the fuel consumption, the sort of immediate fuel consumption based on the power demand. And our fuel consumption goes to a fuel tank block, which really only has an integral block. So it takes a summation of our fuel total based on the changes in our fuel consumption. So an integral block is like the area under the curve. So in that way, we're summing we're taking a calculation of our fuel total throughout our driving cycle. I'll give you a couple of resources that I think you'll find useful for increasing your knowledge for system modeling and system dynamics. This one is a free ebook about system dynamics and controls using Altair Compose. And we talked about Altair Activate today, but Compose is very much underneath everything that happens in Activate, because Compose is our IDE that works with many languages, but mainly OML, the Open Matrix language. And because there is a fair amount of scripting involved in building system models in Activate, it's very good to get a good handle on system dynamics and how to model things like continuous dynamics, discrete dynamics, which we didn't really go over today, but Altair Activate is very capable of this, and so you can take advantage of that using the Compose language OML, and many other useful tools and information, and it goes down deep, and it's free to download from altairuniversity.com. And then a few other links. Altair.com/system modeling applications is a nice hub to learn more about Activate and Compose, and then to also get some customer stories and some videos about other verticals that we didn't really mention, like heavy machinery and hydraulic systems and things of that sort. You can download the products from Altair University. And we have a really nice learning center, altair.com/learning center, that you can use for nice how-to videos and tutorials for all of our tools. And then our forum, community.altair.com. Our forum is where all of our users can post questions and answer questions for other users. And then myself and my colleagues as well answer the questions for our users. So it's a really great resource to search out anything that you're wondering or having difficulty with, and see if somebody already has provided an answer for this. So thank you very much for listening. We appreciate you being interested in our tools. We'd love for you to get going with Activate and our other tools. And if you have any questions, please feel free to reach out and visit our forum and the other resources to start learning more about how to get going using this for your projects and whatever you need. Thank you again.